So, in this class we shall be discussing two more fault simulation algorithms called deductive and concurrent. Now, conceptually they are similar in the sense that these methods try to simulate all the faults at the same time together with test vectors applied one after the other, but the way they work, they handle the faults are distinctly different. So, let us look into these methods one by one. So, the first method that we discuss is called deductive fault simulation. Now, see, these methods have very interesting characteristics. They say that we make a single pass through the circuit, and in that single pass we find out all the faults that are detected by a test vector, which means it is something like this. Let us say I have a given circuit, I apply a particular test vector, let us say T I. What I am saying is that I scan the gates in the circuit just one pass, I evaluate the output, and I can immediately determine all faults detected by T I. This is a very interesting thing. So, I am somehow implicitly simulating all the faults together. So, if there are say 100 test vectors, I have to do this process 100 times, right. So, there is another interesting point is that this method works in event driven mode, like there is a concept of an event. So, for a particular gate, if there is no event occurring, we do not evaluate or process the gate at all. Like say this is done across test vectors. What I mean to say is that suppose I have applied the first test vector T 1, I have processed my circuit, I have found out the faults detected. Now, I apply the second test vector T 2. With respect to the last one, I do not destroy the data structure that you have already constructed with T 1, that remains. Now, I apply the second test vector and I make changes to those data structure only when required. I need not have to re-evaluate all the gates. I find out in which gates the events are occurring, I only make some modification in those gates. For the portion of my circuit where no events are occurring, I do not make any changes. The same data structure as compared to the last test vector T 1 remains. This continues with one test vector after the other. After T 2 comes T 3, then T 4 and so on. So, on the average this runs much faster. So, the concept is that for every line in the circuit, we associate a fault list. So, we shall be defining the fault list in the next slide. Initially, the fault list for all the lines are empty. As simulation proceeds, these fault lists get populated by some information and they change dynamically as we simulate with test vectors one after the other. And as I said, we do not destroy the information after one pass of simulation. We keep it, apply the next test vector and make modifications only where necessary. Okay? This is one way we can speed up the process. Let us see what is a fault list now. Fault list, what it actually means, the fault list Lk that is associated with a particular line k is the list of faults or the set of faults that changes the logic value of line k. What it says is that causes the value of line k in the fault free circuit, let us N denote the fault free circuit, and the faulty circuit N f to differ. This is the idea. Let us take an example, small example to illustrate this. Let us say I have a gate here, AND gate, let us say followed by an OR gate. Suppose we are carrying out simulation with a particular input vector, let us say 1, 0 and 0. Let us say the inputs are A, B and C. This is D. So, we are interested in line D. I shall be showing a complete example later. So, when I talk about the fault list of line D, see D, this is 1 0. So, the fault free value of D is 0 and fault free value of the output is also, let us say F is also 0. Now, LD will contain the set of all faults which will change the value of the line D. That means, it was 0, the value will change to 1. So, in this example, let us see what are the faults which can change the values to 1. You see, one fault can be B stuck at 1 in the previous code. If B is 1, then input is 1 on 1, this line will be 1. So, one such fault will be B stuck at 1 and other obvious fault will be D stuck at 1. So, these are the two faults. So, fault list will look like this. Fault list will consist of all the faults that will change the value of this particular line D with respect to the fault free version. Fault free value was 0. So, what are the faults that will change it to 1, right? Okay. So, there is a process I shall illustrate. We can systematically compute the fault list for all the lines. So, once you have completed the process, what will the fault list for the primary output denote? Suppose you have computed the fault list of the primary output. It will tell you what are the faults that will change the value of the primary output, which actually means what are the faults which are getting detected by the current vector. That will only change the output, right, with respect to the fault free one. So, there are two interleaved steps involved. One is the true value or fault free simulation with a given vector, and we are concurrently computing the fault lists. So, there are some simple set theoretic rules I will be illustrating, using which you can compute the fault lists. Let us take some examples later after we talk about these events. Now, fault lists are computed in an event driven fashion, as I said. Fault list propagation, in the example that I showed just now, here there was one fault B stuck at 1 which has propagated from the input side to the output side, okay? But D was a local fault, right. So, there is a concept of fault list propagation. As I move from the input to the output side, fault lists are systematically propagated, okay. So, for every gate we compute the fault list of the output line and we evaluate this gate only when one of the following these events occur. What are the events? The first event says that one of the input lines of the gate has changed its logic state. This is termed as a logic event. So, I am applying the test vectors one after the other. Let us say in T1 the inputs were 1 0, in T2 it has become 1 1. So, I say that there is a logic event. List event means maybe the input values have not changed, but one of the input fault lists have been modified. When the fault list for one or more of the input lines change. Depending on this, if there is an event, we calculate or compute the fault list of the output. If there is no event, we can simply skip that gate. The rules for computation will depend on the input values, like I shall show with some examples. First example, we take an AND gate, 2 input AND gate with the inputs as 1 1, the output is also 0, 1, output is also 1. So, let us try to say with respect to this gate, okay, this AB need not be primary input, A is coming from some other sub circuit, B is coming from some other sub circuit. So, A will indicate all faults which change the value of A change means to 0, and LB will denote all faults that change the value of B, which means to 0. This is an AND gate. So, under what conditions will the output change? Both inputs are 1 1. So, if at least one of the inputs becomes 0 or both, then the output will change. So, we denote it as LA union LB set theoretic operations. So, either A changes or B changes, then output will be 0. Union, of course, output stuck at 0 will be an obvious fault. This will also be there in LZ. Okay. Take a NAND gate if the output is 0 here, same thing, it will be LA union LB union Z stuck at 1, because now the fault free value is 0. This is a slightly more complex case. You take a 2 input AND gate where the inputs are 0 1 and the output is 0. Now, I am trying to find out under what conditions can the output value change to 1. I can tell output will be 1, well here means obviously Z stuck at 1 is one condition, or this A changes from 0 to 1 and B does not change, B should remain at 1, that means both is 1 1. This I denote like this, L A means A changes and intersection L B bar, B does not change. Now, in set theoretic notation, if you draw the Venn diagram, you can easily prove that L A intersection L B bar is nothing but L A minus L B set difference. You take out all the faults from L A that are common in L B. So, if you have a condition like this, L A is the line where you are trying to make the change minus L B, the line where there is no change. So, if there is another line C, C is also at 1, then it would be L A minus L B minus L C, that means B and C both are not changing. Okay, so, depending on the inputs, your rules will vary. You can see same AND gate, but rules are different, right. It will depend on the inputs. If it is A 1 and B 0, that will be L B minus L A, right. Okay. So, the advantage of this method is that all faults are handled together in a single pass, and therefore, it is faster than parallel fault simulation. But disadvantage is that the fault lists can grow unpredictably. So, memory requirements is typically much higher, and also the set theoretic rules in terms of computing is a little difficult. And the set theoretic rules are possible for many blocks. Let us say, let us take another block like a multiplexer. I shall show that how it is more difficult. So, you can also frame set theoretic rules for simple blocks like a mux. Let us consider a situation where your select line is 0, first input and the second input both are 1 1, and therefore, the output is 1. This is 0, A 0 is selected, it is 1. So, under what condition this F will be 0? First condition is there is an event on line A 0, that means A 0 was 1, it becomes 0. Or there is another condition, there is an event in LS, means S becomes 1, which means A1 gets selected, and there is also an event in A1, A1 is also becoming 0, then this 0 will also propagate, and of course, union F stuck at 0. Okay. So, you can see that as the blocks become more complex, you can have a rule, but the rules can become more and more complicated. Now, let us work out an example, right. Let us see. Let us take an example as follows. Let us say we have an NAND gate, we have an OR gate, AND gate and another NOR gate. So, let us say there are 5 inputs A, B, C, D, E. Let us give some names to the lines F, G, H, let us say output is Z. Let us assume that we apply some input vector, let us say 0, 1, 0, 1 and 0. So, if it is 0, 1, what will be the output of the NAND gate? It is 1, OR gate also 1, AND gate 1, 1 is 1, 1, 0, NOR gate is 0. So, with this values, let us try to compute the fault list for this first test vector. Our first test vector T 1 is 0, 1, 0, 1, 0. So, we start from the input side. See, LA is a primary input, A is a primary input. So, LA will contain only those faults which change the value of A, which means only A stuck at 1, right. Similarly, LB will be, B is at 1. So, B stuck at 0. LC will be, C is stuck at 1, then LD will be, D stuck at 0 and LE will be, E stuck at 1. These are the primary input faults. Now, let us use those rules to deduce the fault list of the other lines. Let us look at line F. You see, F is a NAND gate, inputs are 0, 1, output is 1. So, how the output can become 0? This A has to change to 1, but B should not change, which means LA minus LB, of course, union F stuck at 0. So, if you do LA minus LB, there is nothing common, only A stuck at 1 remains. So, this set becomes A stuck at 1 and F stuck at 0. Similarly, let us do LG. LG. This is an OR gate with input 0, 1, output is 1. So, here again output will be 0 if D changes, but C does not change. So, it will be LD minus LC union G stuck at 0. So, LD minus LC is how much? There is nothing common again, only D stuck at 0 and G stuck at 0. Then comes H, LH. You look at this AND gate, both inputs are 1 and 1. So, the output will change if any one of them changes. So, it will be LF union LG union fault in the output, H stuck at 0. This is LF and this is LG. So, you take the union, there is nothing common. So, A1, F0, D0, G0 and H0. This will be LH, and finally, you compute LZ. LZ is a NOR gate 1 0. So, to make the output 1, H has to change, but E should not change. So, it will be LH minus LE union Z stuck at 1. So, LH minus LE, there is nothing common. So, this remains and this one. And Z stuck at 1. So, we have obtained the fault list for the output line Z. You see, there are 6 faults here. So, what does this mean? It means that for all these 6 faults, the output value Z will change from 0 to 1, which means this test vector T 1 can detect 6 faults, and these are the 6 faults, right. Now, let us suppose we apply a second test vector, where we make the change in one of the bits only. Let us say next example is 1 1 0 1 0, only A changes. So, I am showing the relevant changes in the diagram only. This changes to 1. This is a NAND gate, it becomes 1 1. So, F also changes to 0. AND gate 0 and 1, this also becomes 0 0 0, this also becomes 1. So, you see for this particular gate or the line C D B C D E G, there is no event, neither a logic event nor a list event. So, I need not re-evaluate these again, but we have to re-evaluate a few of the lines. Okay, I am just showing those lines. So, I am just showing it here in the side. So, I need to re-evaluate L A. Now, A is 1. So, L A will be A stuck at 0. This has changed. So, the old list gets removed. Now, this NAND gate is having 1 1 as input. So, the condition for the output changing will be L A union L B. So, L F is recomputed, there has been a list event. List event L A has been modified, also there is a logic event, the input has changed state. So, F has to be recomputed. So, L F will be L A union L B union F stuck at 1. You see L B you take the old value, the previous value. So, L A is now A stuck at 0, L B you take the last previous value and F stuck at 1. Similarly, you compute H, same way you continue. So, you compute the value of L H. Now, the inputs are 0 and 1 AND gate. Output will change if F changes, but G does not change. So, it will be L F minus L G union H stuck at 1. So, you can similarly calculate, and finally, when you come to Z, L Z will be 0 0 in NOR. So, means if any one of the changes, output will change. So, it will be L H union L E union Z stuck at 0. So, this you can calculate similarly. So, you see that here you are just recomputing some of the fault list. A you are recomputing, L F you are recomputing, then L H you are recomputing, L Z you are recomputing, but some of them you are not touching, they remain the same as the previous one. So, this illustrates event driven simulation, right. So, we are not simulating the whole circuit, but we are simulating only those parts which are required. Okay. So, let us move to the last method that we shall be discussing on fault simulation, is the concurrent fault simulation. Now, concurrent fault simulation is based on the premise that during simulation most of the values in most of the faulty circuits do not change, that on the average only a few lines, a small percentage of the lines, they change in their logic values. This is the observation. So, here again, just like in the previous method, we consider all the faults, but we shall see we maintain much more information here. We maintain not only information about the faults, but also the input and output values of the gates. So, essentially we simulate the fault free version of the circuit and each of the faulty version concurrently. That is why it is called concurrent fault simulation. I shall be explaining this with an example. So, we simulate the good circuit, and for every faulty circuit you simulate only those for which at least one of the input or output values are changing with respect to n. So, I shall be illustrating this with the help of an example. Let us take a 2 input AND gate with the inputs 0 1 and 0. Okay, here also we maintain a fault list, but as I said, the nature of the fault list is more elaborate. We keep information of not only the faults, but also the input values and the output value. So, for this particular gate, you see A is 0, B 1 and C 0. So, what are the faults which can change at least something? One is A stuck at 1, this input can change. If this fault happens, the input will become 1 1 and the output will be 1. B stuck at 0, B is 0, input will be 0 0, but the output does not. You see here, even if the output does not change, we keep it in the fault list. And lastly, C stuck at 1, but input is 0 1, but the output is 1. Okay. Now, in many textbooks, this same information which is shown in a tabular fashion like this, it is represented like this, as if this is the fault free version of your gate and these are the 3 faulty versions. It is shown like this. So, you are simulating them together, you are simulating the fault free version as well as these 3 faulty versions which change at least one input or output lines of the gate, right. This is the idea. Now, how are the fault lists updated here? Fault list will be updated if one or more of the following conditions are satisfied. Firstly, of course, the fault is local to the gate, or the value implied at least one input or the output of the gate is different from that in the corresponding fault free version. Now, I shall try to explain this with the help of an example. And at the beginning, all lines are in an unspecified state x. As simulation proceeds, the values get defined and the fault lists get updated. Okay. So, the advantage of this method is that you see here there are no complex set theoretic rules. So, on the average it runs faster as compared to deductive fault simulation, right. Here we can also include delays of the gates. But the problem is that here the fault lists are much more elaborate. So, memory requirement is higher than compared to deductive fault simulation. So, you need more information to be stored. So, let us illustrate this with the help of an example. So, we take a simple example here. Let us take a circuit consisting of 3 gates. The inputs are A, B, C and D. This is E, F and the output is, so this is a NAND gate, output is G. So, let us name the gates G1, G2, G3. Now, one difference is there with respect to deductive fault simulation, because in the earlier case we defined the fault list corresponding to each of the lines, but here we are defining fault list for the gates, not the lines. Okay. This is one difference. So, let us try to simulate this circuit with the input value, let us say 0 1 0 1. So, this value is 0, this value is 1 and this value is 1. I am just showing you for one simulation. For this case, level by level you process the gates. First look at G1, I am showing the fault list for the different gates for G1. G1 the inputs are 0 1, output is 0. So, what will the fault list contain? One fault will be A stuck at 1, for which the inputs will be 1 1 and the output will also become 1. Second fault is B stuck at 0, input is 0 0, output is 0, and third one is E stuck at 1. So, input is 0 1, output will be 1. This is the fault list for gate G1. Similarly, the fault list for gate G2 will be like this. It is 0 1 1, this is an OR gate. So, there can be a fault on line C, C is stuck at 1. So, it will be 1 1, no change in the output. D is stuck at 0, 0 0, output will become 0, or F stuck at 0, input is 0 1, but the output is 0, right. Now, let us come to G3. So, here we shall see how fault lists are propagated. Okay, first let us look at the local faults 0 1 and 1. So, the faults will be E stuck at 1, F stuck at 0 and G stuck at 0. So, if you have E stuck at 1, input will be 1 1, NAND gate, output will be 0. F stuck at 0, 0 0, output 1, and this 0 1, output 0. So, I am showing it separately because these are the local faults. Now, we come to the propagated faults. You see propagated faults I am showing by a different color. You see here there is an event on line E if this 0 changes to 1, right. So, I have considered the local fault here, but this E might be changing to 1 because of some fault in G1 also, which changes the output to 1. So, look at G1, see wherever it changes to 1, it is here and here, right, these two faults. So, these two faults will get added to this list. So, both A stuck at 1 and E stuck at 1 can make this first input as 1. So, this will can make it 1 1, this E stuck at 1 also can make it 1 1. So, the output will be 0, right. So, these two faults, these have been propagated from G1. Similarly, look at F. Well, you have already inserted F stuck at 0 local fault here, but F might become 0 because of some fault which is there in G2, which are this and this. So, also add those two faults, D stuck at 0 and F stuck at 0. So, this will become 0 0. These two faults are from G2. So, you see that in this way you can proceed, you can compute the fault list finally. So, when you reach the fault list of the final gate output, you know that the fault free value is 1, you look at all those faults for which the output is coming as 0, like one is this, one is this, one is this and one is this. So, you can conclude that this particular test vector detects these 4 faults, right. And when the second vector is applied, we follow a process which is very similar to the deductive fault simulation. Same way you proceed, same way you modified the fault list. If there is no event, do not make any changes, same way. Okay. So, we have actually illustrated 2 methods of fault simulation, where we have seen that we can simulate all the faults together. It is pretty fast, but memory requirement is higher than the earlier methods we mentioned. Okay. So, in our next lecture that will follow, we shall be looking at the other processes of testing like test generation, design for testability, etc. Thank you.